Hi everyone, my name is Brian Drawert, and I'm here to give part 2 of this talk. I hope you've listened to Seth Chandler's talk and gotten some good information on how we were doing modeling of public pensions using Mathematica. I'm going to talk about how we took that Mathematica and moved it to the cloud. So first I'm going to talk about that process we used to move the cloud. Particularly I'm going to talk about a process we used to integrate Mathematica and Python using a language Pythonika, although I found it very interesting that Stephen Wolfram today talked about that they're going to have a Python integration in one of the newer versions of Mathematica. So it seems like that with their cloud technologies and their language integrations that we are on the right track if Mathematica is doing exactly what we're doing. So I'm happy to see that. So after that, I'm going to talk about cloud computing a little bit more, and then talk in detail about how we develop the pension calculators as a service and detail of that. But I'm going to try and save enough time to give an actual live demo of this pension calculator service. So cross your fingers, and I hope that goes well. So talking about moving from Mathematica to the cloud. We wanted a widely accessible platform, and what we found was that we wanted to build a web app on the Google App Engine or app scale cloud infrastructures. And I'll talk more about them later in the cloud portion of my talk. But what we had to start with is Seth Chandler's pension computation model in Mathematica. So our very first attempt was to integrate the app scale web platform with Web Mathematica. We rejected that after some initial attempts based on its limited ability to scale up and down. And our solution was to rewrite the whole engine in Mathematica. And the tool we use there is Pythonika. Pythonika it's a MathLink module that allows you to run Python code directly from your Mathematica notebooks. It automatically translates all the data types back and forth, and you can even write and define Mathematica functions right in the Mathematica notebooks. It's an open source project. It's hosted on the code.google.com, Pythonika, but I'm also hosting a fork of that for the updated version 9 of Mathematica, and any contributions that you guys have, or if you have any questions about installing, please don't hesitate to contact me. I want to try to support this and keep it going in the future. So I want to show you a little bit about how how to use Pythonika from within the Mathematica notebook. So when you need to install Pythonika, and I'm not going to go through that here. It's kind of boring and a little bit detailed. But I, of course, am a Unix user, so installing stuff in user local bin is what I typically do. So you have an executable, the Pythonika executable, installed there. You simply use the install functionality to install that app. If you check your links of that app, you see there's a link object with some connection numbers. And if you need to uninstall it or clear out the kernel, the uninstall function does that as well. And then, of course, the links are gone. So you'll need to do the install on every time you do the Pythonika notebook. Every time you want to use Pythonika within one of your Mathematica notebooks. So once we have that installed, we're able to use Pythonika to run Python code and move variables back and forth from Pythonika. So the first way we do that, so let's say I have my pension calculation Python library in the same directory as my notebook. So I can call my notebook directory and get the libdir variable in Mathematica, and then the to_py says I'm going to take that libdir variable and make a Pythonika variable called libdir. Then below that, next to that, I'm going to call some just random Python. So import OS and sys is just importing some basic Python libraries. Import NumPy. For all of our computation, we use NumPy as the very powerful numerical computation for Python. And then if you want to use a bigger string, I say, well, if libdir is not in my system path, add it to the system path, just to make sure it's there. Once that's all done, I want to load my pension calculation module. If it's already loaded, let's delete it. And then let's say from pension calc, import the pension calc. So everything I've done here is just running regular Python code, but I'm doing it from the Mathematica notebook. So I have a nice Mathematica interface to my Python code. That's all great, but what I found was super useful was the setting up functions or writing functions in Python that were Mathematica functions. So for that, I use the PyFunction directive. So I'm going to write out the benefit side py function, defining it as a py function. And then the first line here, we have benefit side py, def benefit side py is the Python version of how to define a function. Then it takes a set of variables. You see best salary vector, final average salary vector, cumulative contributions, refund rate, inflation. So that's all the input variables you're going to take for that function. Then all I'm going to do is say pensioncalc.benefit side. Take that library that I loaded in the previous slide, pass through all the NumPy converted arrays that were passed into this, and that's just going to return me back a type. So this is just a very shallow, easy wrapper to run a piece of Python code and return it back. Now, one of the things I had to do was make sure that typing was correct. So the 11th element of my array, return ret10, I needed to return as type int. And then because you need the basic types of Python are supported, but not necessarily a NumPy object, which is what actually the pensioncalc.benefit side is going to return, I need to convert each of these items to lists for every item in return. So this small little function here allows me to take all the data vectors in Mathematica and pass it through down to my Python function and call that and return back all the data arrays. So the Mathematica side function is very similar. I'm just going to show it for comparison. Takes in exactly the same data arrays and then set up as a compiled module. So this is written by Seth, my colleague. And the complex data structures are all preserved. So this is the actual Python code that's returned, and you see there's quite a few different inputs and quite a few different outputs for each of these benefit side. And what this allowed us to do was to take identical parameters for both the Mathematica code and the Python code and run them together. So here's just a few of the parameters that we used to set up that sort of benefit side computation. Then, to run the Python code, it's as simple as just calling the benefit side py function with all those input variables, and you see we get back very complex data structures. But the real purpose of all this was to use this as a unit testing infrastructure. So to run this unit test, I simply called the Mathematica side code with all of the input variables, double equals the Python side code, and if that returns true, then every single element of every single one of those lists of lists is identical between those two things, and our two codes are identical. And so what this allowed us to do was to make a robust collaboration together with the Mathematica for rapid prototyping and development and the Python for the web application development. And this wasn't just the single iteration of writing at one time, but writing it over multiple iterations as we accounted for the new policies and for additional pension plans and their extremely difficult complexities. So there are over 50 plus functions were converted this way, and then Python library is over 2,000 lines of code. So it was quite an endeavor when it was all said and done. I, of course, have to plug other parts of Python or Pythonika or other reasons why you would want to use it. And the basic premise is that you want to enhance your Mathematica notebooks with software that isn't necessarily part of Mathematica today. And there's a lot of those pieces of software, but the one I want to plug is the PyURDME, something I'm working on. URDME is a spatial stochastic simulation software that running biochemical systems for discrete biochemical systems. In particular, we published that in the Systems Biology Journal last year. And you see I have a couple of diagrams here of yeast cells or neurons or E. coli that we used. So if you want to do spatial stochastic simulation, and very soon PyURDME will be able to use in your Pythonika, your notebooks via Pythonika. All right, so I've gone quickly through some of the Mathematica stuff, and now I want to talk about the cloud computing end of things. So when we talk about cloud computing, there's a lot of confusion. People use the word without regard to its formal definition. So I kind of want to give a formal definition here. And cloud computing is really resources required on demand, the resources that are pooled across multiple customers. So you have a bunch of computers together, and you get some of them. Some people get other of them. But the big important parts are the rapid elasticity. I want a server, and I get it in 1 minute from now. I'm done with it. It's gone. And the metered service. I only pay for what I use. I don't have to pay for electricity or for servers that I'm not using right now. Cloud computing is typically one of 3 different stacks, and sometimes the cloud computing pyramid, I don't know if you've seen that before, but it's pretty popular. And so the 3 stacks are software as a service, platform as a service, and infrastructure as a service. Infrastructure as a service is kind of the most common one, at least the most well-known one. That's when you rent servers. So you're getting a cloud service, infrastructure as a service. So servers, storage, network, operating systems as a service. And the public cloud providers, particularly Amazon EC2, is the most well-known, although Microsoft has their offering, Rackspace, Google Compute Engine, and there are dozens of others. What isn't quite as well-known is the private cloud. You can have infrastructure as a service on your own hardware. You can set up your own service. And there are a couple of different softwares out there that are open source and publicly available, such as OpenStack, Eucalyptus, or CloudStack, that you can install those and have your own IaaS. So software as a service is probably the second most well-known. That's on-demand software for end users. It's delivered over the web. So this morning we learned about Mathematica Online. That's software as a service. You no longer have to download and install Mathematica. You simply go to the web URL for the online Mathematica. You run it. When you're done with it, you close your browser and you put it away. Centrally managed, no install, no upgrade is very powerful for a distribution of software. And like they said, you get a lot faster turnaround time in development. And it's metered, subscription or pay-as-you-go. And Salesforce, Google's Gmails or Google Docs, the Adobe Creative Cloud, and Microsoft 360 are all good examples of software as a service. But the least well-known of the three of the software stack is platform as a service. And it's platform as a service. It's a platform for web development. It allows for rapid development and prototyping, and it abstracts away the complexity of having multiple services. And scalability and load balancing are a very important part. When you get a website, you might only need a single server now, but what if you get a spike and need 10 servers or 100 servers or 1,000 servers tomorrow? Do you have the ability to scale your website to that level? Platform as a service gives you that ability to scale up and scale down easily without having to ever write it from the beginning. Google App Engine is probably the most well-known. Heroku and Microsoft Azure are versions. My company, AppScale and OpenShift, are two private platform as a services. And I also wanted to mention that this morning we learned about the Mathematica programming cloud. That's also platform as a service, right? So you're going to develop your web app, your app, however it is, and you're going to deploy and distribute it through their platform, and it runs on their infrastructure. And it's a really great way to manage your applications. So Google App Engine is a platform as a service where you run on Google's cloud infrastructure. So Google has one of the most advanced number of servers out there, and advanced network and storage system. So you get to run your app on their infrastructure without having to worry about dealing with any of that. And it's a pay-as-you-go system with automatic scaling and load balancing, with a bunch of useful services like user authentication, high replication data store, and task queues, all stuff you're going to use, but you don't really want to have to worry about building yourself. Currently, they support languages Python, Java, and Go and PHP are experimental, but of course, we're going to focus on Python today. So the AppScale is the private platform as a service that you can run. It's API compatible with Google App Engine. So you're going to run your Google App Engine apps on any public or private cloud infrastructure that you can set up. And it's open source, which means it can be customized. So here's where we can deviate from the just normal platform as a service. And some things we did in this project to work with AppScale was, of course, Python, where you can optimize, get a static compiler for optimizing Python. And just the column matrix computation, we did a benchmark. The Python code was 27 milliseconds, Python 15 milliseconds. So you're getting about a 50% speed up with no change in your code. However, you can't just run that on Google App Engine. We had to modify that to integrate it with AppScale, modify AppScale to integrate that in. And the other thing we did is a proof of concept to see if we could get the Mathematica code to work. We wrote a Java JLink integration layer into AppScale, and then wrote the ability to expose that ability for our web apps to then call that. So we could just write a Python web app, have it call and execute Mathematica code, return the result to the user. So that was a quick introduction to cloud computing. So now we're going to talk about the pension calculator service. Seth talked about this in detail, but the basic premise is that we wanted to enable plan members and plan managers to analyze the cost and benefits of various plan parameters. And the idea is to democratize the ability to analyze these complex and very emotional and political issues. And Novum is a nonprofit and non-advocacy. So the point is we're not taking sides. All we're trying to do is give everybody tools so that we can have informed discourse about all of these, about the pension crisis. So this means that we want to have non-experts analyzing pensions. That means we need a UI that gives intuitive control of the pension parameters. And as you can imagine, pensions are very complex, so we don't want to overwhelm users with the mass complexity that we've seen from the pension systems. So our idea is to present a widely accessible web interface for public use, and then we're going to have a Mathematica package for researchers, as well as an open API for web development or for web access of researchers as well. So the pension calculator as a service structured is basically this way. So the user on their laptop is going to just access the web UI over there, over the web. The web UI is just HTML and JavaScript. It's going to make REST calls back to the centrally cloud-located API, which is going to return its data in JSON format. Then it's going to plot that data using the high charts library, which I'll show you guys that next. That API receives a request to do a computation. Then it queries the pension database, where we have the database of all the various plans that we've integrated into our system thus far, ties together that data with the request data, and calls the pension computation engine, which does its computation of the benefits over the costs, returns that back to the API, and returns that back to the user via the web API. Or if we have a tablet or mobile version, that will call the API directly, or the researchers will be able to call that API directly as well. So now, hopefully, this is going to work. Control minus? I don't think that works. There we go. Here we go. OK, so this is the live pension calculator. It's running on my local installation of the Google App Engine SDK. And you can see that what we're displaying here isn't a static number. What we're going to display is the present value of your pension wealth over time. So if your entry age is 25 and some of the additional parameters we'll show in a second, the present value of pension wealth shows a very non-linear increase in how it works. So I can put my cursor over here, and it'll show you John is, I can't read it on there. John is 68 years old, and his gross pension wealth is $67,000, or his net pension wealth, $670,000, or his net pension wealth is $475,000. So let's say I change the entry age up by 1 year, click Done. The web UI makes that RESTful call back to the API. It does a computation and returns back these new curves. So the original curves, the solid regions, are still there for comparison, but the lines are the new plan. So let's change something else. So right now we're using your starting salary of 40K with a final average salary of 3 years and salary growth of 1.2%. But let's say you have a current salary of 49K, and you've already worked there for 10 years, and your salary growth is 2%. Click Done. Gives me a new computation. The benefit multiplier is, of course, one of the most important ones. What percentage of my final average salary am I going to receive? Employee contribution. One of the more interesting ones is retirement thresholds. So we talked about normal retirement. So if you retirement thresholds of 65 years with 5 years of service, or 60 years with 20 years of service. But what if I want to add, if you're just, say, 65, did that actually work? No, there we go. Or there's early retirement thresholds. Now, early retirement says you can't actually get retirement before these specific thresholds. So that's 55 and 5 years of service, or 30 years of service. Let's add one that's 30 years of service and 70. Sounds good. So it's going to do all these computations right on the fly. The other side of this, let's see if this actually works. Excellent, is the cost side. So with the cost, what we're going to show is the past cost data. So this is actual data we have from the defined benefit pension plan, and the projected future cost. And what we're showing there, the dotted line is the 50th percentile, the mean, and then the top and bottom line above that are the 25th and 75th percentile, based on an 8% expected return. So if your return is better than that, you're going to get a lot cheaper. If your return is less than that, it's going to be a lot more expensive. Now, with this, with the cost, it's not a single employee, but in fact you have multiple current employee groups. So for the teacher retirement system in Texas, there was 2 different current employee groups. Teachers that were hired before 2007, which had one set of defined pension plan, and then after 2007 they changed it, and we needed to get a new employee group. Plus, there's a group of employee retirees, plus we're going to have all new hires actually are going to have under a entirely new plan, giving you the option to change parameters for all 3 of these. So new hires it's basically the same as everything I just showed you on the benefit side. The retirees, the only thing you can change because they're already taking a pension is the cost of living adjustment that they incur. But the current employees have a few things. Let's say you're in trouble. Let's crank down the benefit multiplier to just 1%. They're not going to be happy about that, but we're underwater. What are we going to do? So we compute it. Now, of course, giving a demo. Oh, it did not do what I wanted it to do. It did do something, yes. So now we have red lines, which are the new plan versus the old plan. So this takes about 22 seconds on my MacBook Air, which is not quite as fast as the Mathematica version, but we're doing a little bit more computation, and the Python this is not the Python optimized, and the Python is not quite as fast as the compiled version. Okay, so I see that I'm being, okay, yep, so now we have a new curve. Okay, so I just want to say thank you to Novum, the Laura and John Arnold Foundation, Seth Chandler for inviting me to the talk, and Wolfram and the Mathematica community, and everyone here for listening to my talk.